So, related rates of change. Rates of change. What's another word for rate of change? Slope. Another word. Slope for tangent line. Velocity. Acceleration if it's of the velocity. All of these things. What's the word that starts with the D that we call this in calculus? Derivative. Related rates means related rates of change. Rates of change are derivatives. Related derivatives. Related derivatives. Derivatives that are related. Now, related for us means in the same equation. We're going to have more than one derivative in one equation. That's how you relate derivatives, is by having more than one derivative in one equation. So, we're all familiar with area equals pi r squared for a circle. Now, what if the radius is not a constant? What if it's increasing with time? If the radius is increasing with time, what's the area of the circle doing? Increasing with time. Now, the rate of change of the radius would be a derivative. The rate of change of the area would be a derivative. Because see, if the radius is changing with time, that means the area is changing with time, which means the radius and the area are both functions of time. The size of the radius depends on the time. The size of the area depends on the time. So, if the radius is changing with time, that means that the radius and the area are both functions of time. We could write it out. R equals blah time plus blah squared. All right, that's a function of time, isn't it? So area then is, let's see, what can we use besides blah? Yeah. How about meh times time? We'll square it just for fun. Minus blah divided by meh. Some function of time. Okay? Now, our mission, if we choose to accept it, is to relate these rates of change, relate these derivatives. And we do that by using implicit differentiation. Yesterday, with implicit differentiation, our function was always called y. Today, with related rates, our function can be called anything. And they're almost always functions of time. Almost always functions of time. So, if I'm going to treat a as a function of time, when I take its derivative, I can call it dA dt. I don't know what the derivative is yet, other than I can call it dA dt. Okay? And then when I take the derivative of pi r squared, but remember, so a is not a variable, because a is a function of time, so treat a like we did y yesterday. R is not a variable either, because it's a function of time, so treat r like we did y yesterday. So the derivative of pi r squared, all right, r is a function, so we've got to, if we had pi times u squared, we'd use the general power rule, right? We'd make that 2 times pi times u to the 1 times the derivative of u. So 2 times pi times u to the 1 times the derivative of r. You with me? Look what we've done. We now have related rates. We have dr dt. That's a rate of change. And we have dA dt. That's a rate of change in the same equation. So dr dt, the rate of change of the radius, and dA dt, the rate of change of the area, are related by this equation. Now, they're going to have to give us more information. They're going to have to either tell us what R equals and tell us what the rate of change of R is so we can find what the rate of change of A is, or maybe they tell us what the rate of change of A is and what R equals and ask us what dr dt. You see what I'm saying? There's three different things we don't know now. We don't know that, we don't know that, and we don't know that. They're going to have to give us enough information about two of them for us to figure out the third one. Okay? But we've got, this is why this section is called related rates, and this is why this kind of problem is called related rates. We have related the rates of change of radius and area with this equation. Okay? You with me? All right, that's all we can do with that equation right now. What if we had this? They're all functions of time. Mm-hmm. Yep. So, use implicit differentiation. V is a function of time, so its derivative is dv dt. And I do recommend trying to use this dv dt notation instead of v prime. You can go v prime if you have to. All right? Now, to find the derivative of the right side, 1/3 is a constant. Pi is a constant. So I'm using the constant multiple rule. That's a constant. So the derivative of the right side is 1/3 pi times the derivative, or times whatever the derivative of r squared h is. Okay? So it's 1/3 pi times whatever the derivative of r squared h is. All right, now let's find the derivative of r squared h using the product rule. Remember now, r is a function, h is a function. Okay? So, product rule. First function, r squared, times the derivative of the second. H is a function, so its derivative is h prime, or dh dt, plus the second function, h, times the derivative of the first. R is a function, so its derivative is 2r times the derivative of r. So 2r times the derivative of r. Yes? Exactly. Right. That's why I'm calling this d whatever dt instead of like d whatever dx. Because, and you have to be told this, or given enough information to figure it out on your own, that these are functions of time. Okay? You don't just wake up in the morning and go, I'll bet h is a function of time today. No, that you have to either be told it, or from the context of the scenario they give you to solve, realize it's a function of time. Guess what they are in this section? Functions of time. Okay? So there's your clue. But yeah, so that, everything you said is exactly right. Okay? All right, so y'all with me? Now, for one like this, they got to give us a lot of information, don't they? For us to be able to work with it any. They got to give us a lot of information because there's too many unknowns. dv dt is an unknown. R is V is an unknown. R and H are all unknowns when we start. Then dv dt is an unknown. dh dt is an unknown, and dr dt is an unknown. So, and then look, in our new equation that relates those three different rates of change, we still have an R and we still have an H, and they're still unknowns. Okay? So they got to give us a lot for us to be able to solve for something. You think you're with me on the concept? All right, there's some guidelines for you on page 150. figure out what you're given and what you need to know. Figure out what you're given and what you need to know. Write an equation involving what you're given and what you need to know. Then use implicit differentiation. Then they've given you some information that you can substitute into your related rate equation. Okay? But you got to figure out what you know and what you need to know. And write those as variables. You know, if they give you radius, call it R. If it's a function of time, call it T. Make things make sense. Okay? So you need to know, what you need to know. That's step one. Write an equation involving what you know and what you need to know. That's step two. Take the derivative. That's step three. You got to use implicit differentiation because everything's a function. I say everything. They might give you something that's a constant, but everything's a function of time. And then substitute in either information they give you or that you can figure out yourself to replace some of those unknowns. All right? I write them this way. Once you figure out what you know, write a variable expression for it. Once you've figured out what you need to know, write a variable expression for it. If you can draw a diagram, draw a diagram. Not everything has a diagram, okay? But if you can, draw one. Write an equation with your knowns and unknowns. Use implicit differentiation. That's how it becomes a related rate equation because your derivatives are the rates. Substitute in everything they tell you or you can figure out. Solve for what they tell you to solve for. Number 2, on page 154. In exercises 1 through 4, assume that x and y are both differentiable functions of t. So we already are used to y not being a variable. In this particular equation, x isn't either. Now, unless they tell you x is a function of time, don't go around assuming that x is always a function of time. It's not. It never has been up until now, has it? So if they got to tell you that it is for it to be, don't, because man, everything we've done up till now would be wrong if x was always a function of time. So they told us x is a function of time, and find the required values of dy dt and dx dt. So for number 2, they give us that y equals 2 times the quantity, x squared minus 3x. And in part A, we're supposed to find dy dt when x equals 3, and find dx dt when x equals 2. Now, regardless of what they tell us to find and what numbers they give us for things, we start off this problem. In fact, let's pretend they don't tell us anything. That might be the safest bet here. Just pretend that we're supposed to come up with an equation to relate the rates. Okay? So, finding our knowns and unknowns. They've done that for us. They're calling these things x and y, and we don't know anything about any of them. But they've already given us our equation. So they've skipped down to here for us. So we're starting this at step 3. Okay? They've already figured out that our unknowns are called x and y, and they've already figured out what the equation relating the x and the y is. Okay? So we're starting at step 3. So what we're supposed to do next is take the derivative. That will turn this equation into a related rate equation. So the derivative of y is dy dt. You can call it y prime if you have to, but it's dy dt. Okay? Equals. Now, 2 is a constant. 2 remains a constant. So I'm using the constant multiple rule on the right side. It's going to be 2 times whatever the derivative of the parentheses is. It's 2 times whatever the derivative of the parentheses is. So let's concentrate on getting the derivative of the parentheses. the derivative of x squared. Up until 2 seconds ago, the derivative of x squared was always 2x. And it still is if x is your variable. But x isn't our variable, t is. How do I know t is our variable? Because x and y are both differentiable functions of t. They told me that it is. Okay? So the derivative of x squared is 2x times the derivative of x, which we're going to call dx dt. You can call it x prime, but that's really weird looking. Call it dx dt. Alex?
Why could you multiply 2 to x squared and 2 to 3x?
I could. I think it's simpler to use the constant multiple rule. Okay? All right, you with me this far? Now I've got to take the derivative of negative 3x. Well, it's constant multiple rule here again. It's negative 3 times whatever the derivative of x equals. What's the derivative of x equal now? Dx dt. I know, it's hard to think of x as a function, isn't it? But it is. Not because I say so either. Because now Newton doesn't even say so. The person who made up this problem said so. Okay? So it's not automatic. Don't assume that from here on the rest of the year, x is a function of t. It's not. X is your variable. Unless they tell you that it's not. And they told us it's not. They told us that it's a function of t. Okay? So you with me on this first step, the derivative step? All right, let's clean it up a little bit. I like dy dt on the left, but now I think I do want to distribute that too, Alex. So I'm going to multiply 2 times 2x dx dt and get 4x dx dt, and then 2 times negative 3 to get negative 6 dx dt. And I think there's even one more step of simplifying I want to do here. I think the work would be simpler. Hang on. I think the work would be, I don't want to take out a 2, I just multiplied it through there. I think the work would be simpler if I had 1 dx dt instead of 2. How can I get 1 dx dt instead of 2? Factor out the dx dt. So dy dt equals the quantity 4x minus 6 times dx dt. Now, you can put the dx dt in front if you want to. Now, part A. We're supposed to find dy dt when x equals 3 and dx dt equals 2. So I rewrote that to say exactly what I just said. Find dy dt when x equals 3, given that dx dt equals 2. So, we've got things we can substitute in now, don't we? We can substitute 3 in for x, and we can substitute 2 in for dx dt. So dy dt, still on the left, equals. Instead of 4x minus 6 in the parentheses, they tell us that x equals 3, so it becomes 4 times 3 minus 6 in the parentheses. Times dx dt, they tell us that dx dt equals 2, so times 2. Well, 4 times 3 is 12. 12 minus 6 is 6. 6 times 2 is 12. So dy dt equals 12. Depends on how much information they give us. If they give us every unknown, we'll get a constant. All right, part B. Part B wants us to find dx dt when x equals 1 and dy dt equals 5. Yeah. So look, this is our related rate equation. We're just using it for a second problem. We used it for problem A, now we're going to use it for problem B. So substitute in what they give us, and then we'll solve for whatever's left. So we're going to find dx dt. So dx dt is our unknown. When x equals 1, so replace x with 1, and dy dt equals 5. So replace dy dt with 5, and it looks like that. So solve it for dx dt. Not the worst thing in the world. Now, related rates are the kinds of problems that really can just twist you in a knot. They really can. And the problems that I'm going to assign you are ones that I think you have a reasonable chance of success on. There are 54 related rate problems in this section, and we're not doing anywhere near all of them. Okay? And there's a reason, and I picked out the ones that I wanted to pick out. Later on in the year, I think we can do more of these successfully. At this point in the year, I chose carefully. Okay? So, if you master what we're doing here in the next couple days, you know, don't go strutting through Murray State telling all their college calculus students that, I think related rates are easy. Because they're not. They're really not. Okay? And this is the kind of thing that I have had several students in the past from whatever college they've been at come back to me and say, can you explain related rates again? Because it just takes a while. So I'd already explained it to them once. They went to college, that teacher explained it to them, and they came asking me again, not because I'm better than that teacher at all. They just thought hearing it again might help. It takes a while. Okay? And I taught calculus for years and years and years before I thought related rate problems were easy. Everything else I thought was easy after, fairly quickly. Once I taught it and really had to think about why it all works the way it works, calculus started making sense to me. Related rates took a while. All right? And I can still get twisted around on a related rate problem just like you can. It all boils down to, though, remembering what it all is about. You've got to get an equation that relates your knowns and your unknowns. You take the derivative of it, and now you've got an equation with rates in there. You've got to be given enough information to work with it after that. Okay? So, now I'm telling you, I think these problems are difficult. I've had enough really, really bright students over the years think these problems are difficult so that I think these problems are difficult. I also think they're doable, because I've had a whole lot of students over the years figure these out. Okay? Let's look at number 7. I mean, come on. Wouldn't be a fun day if we didn't do anything with trig in it. A point is moving along the graph of the given function such that dx dt is 2 centimeters per second. They just told us something. They told us that dx dt equals 2 centimeters per second. Find dy dt for the given values of x. So don't worry about the given values of x yet. They give us our equation, y equals the tangent of x. And we have to find dy dt. So again, they're doing part of the work for us. We're not having to search through a word problem yet, figure out what we know and what we don't know, and come up with an equation relating them. They give us step 3. Okay? So we're starting at step 3. We have this equation, y equals the tangent of x. I can take the derivative of that. We could have done this part yesterday, except for the very end of it. So yesterday, wouldn't we have said, oh, the derivative of y is y prime. Call it dy dt. Then we'd say, the derivative of the tangent of x is secant squared x. That's where we would have stopped yesterday, right? Because yesterday, x was our variable. But now, they tell you, when they tell you that there's a rate of change called dx dt, there must be a function x, called x, that's a function of t. It's the only way dx dt can exist. If you've got a dx dt equals 2, there must have been an x equals something above it before you took its derivative, right? So they're telling you, when they tell you dx dt equals 2, they're telling you dx dt equals 2, and they're telling you x is a function of t. So now I've got to take the derivative of x. I've got to chain rule it. Take the derivative of x, call it dx dt. Make sense? We now have, so we started with an equation. We now have a related rate equation. It's an equation with rates in it. The rates, dx dt and dy dt, are related by this equation. All right, I don't like working with secant squared, so what am I going to turn it into? Not secant x times secant x. What? Yeah, I'm going to go with 1 over cosine squared. Okay? Everybody good with that? Now, substitute in everything we know. We haven't yet used the fact that dx dt equals 2, have we? Replace that dx dt with a 2. So I've got 1 over cosine squared x times 2. So can I call that 2 over cosine squared x? And now we answer the 3 questions they want us to answer. We're supposed to find dy dt when x equals negative pi over 3. So we solve that one by replacing x with negative pi over 3. Part B, we replace x with negative pi over 4. Part C, we replace x with 0. And the rest is, no, I was going to say hard labor, but it's stuff you already know how to do. I'll give you that. Yes. Yep, to do that in your calculator, you'll have to do parentheses, cosine x, close the parentheses on the x, then close the parentheses that was in front of the cosine, then put an exponent of 2 on it. All right, I think you can do that. So take a mental picture of those answers, or you can look at the video tonight. There it is. See it? See it on the video? Oh, there you go. Number 10. All right, we're not going to finish 10, but we're going to start it. It says, using the graph of f, determine whether dy dt, we're not going to have time to get enough done for me to explain it. So, there's your assignment. I don't think you can do them all tonight. I don't think, but maybe you can. You should be able to do 1 and 3. And 6, 7, 8. And try them all. I don't know. Maybe you can do them. 15. Oh, give them a shot. Give them a shot. I know you can do some of them. I think you can do others. Okay?